I feel like I got this out of here, so I should do that. Oh, I see it. The pop out, didn't I?
Literally all just sitting there quickly. And I think the grad student was like, this 6'8", like, I'm fine. You guys think?
Okay, well, okay. Last time I figured out how to pop it out, so hopefully it's big enough. Big enough in the back to see what I wrote. Okay, cool. Sorry, I don't know how to get rid of. But I've forgotten. There's different buttons. I don't know what's going on. How's everyone doing? Good. Okay, good. We made it to Friday. Congratulations. Cool. Well, we didn't get as far as I wanted to last time, so hopefully we'll do some more examples today. But maybe I'll call on someone to do a very brief summary of what happened last time. So let's see. Eric, would you like to help us out here?
Talk about dihedral groups.
Perfect. And what are dihedral groups? Anyone, it doesn't have to be Eric, but if you have an answer, that would be great.
Rigid mesh.
Yeah, very good, very good. Excellent job on a regular polygon. Very good. So that's what we talked about last time. Are there any, yeah, we talked about the dihedral group as an example of a group, which were the symmetries of a regular n-gon. And we said it has this nice representation where it's generated by two elements, R and S, that have that obey these identity principles. So, or these relations. I think one of the homework exercises has you show that this representation is equivalent to a slightly different representation, but also with two generators. And so that's kind of written out there. So there's other representations, kind of like what was alluded to last time by Peter. There's other ways you can represent this group. And the generators and relations just look a little bit different, but that's the one we talked about last time. Any lingering questions? Okay, we also introduced the idea of a symmetric group. And right now we started talking about the symmetric group on a set. So if we have a non-empty set, capital omega, that's what that weird big, I don't know, house thing is. This thing is a capital omega. So S sub omega is a set of bijections from omega to itself. So that's bijections are, of course, injective and surjective functions, right? So if I pick a function from omega to itself, it's injective. If whenever the outputs were equal, it turned out the inputs were actually equal. So two different elements aren't going to the same place. It's also surjective if I hit every element in the codomain. So everything in this codomain is hit by some element in X by F. Okay, so this thing, the set of all of these functions, these bijections from omega to itself, is a group, and it's a group under the operation of function composition. And we said last time that the identity operation, or the identity element then, is what element? Yeah, and one meaning like the identity map, identity function, right? So here the identity, very good, is the function that takes like X and maps it to X, right? Just fixes all the elements. Okay, and So what are inverses? Well, they're the inverse functions, right? And what's nice is that every bijection has a well-defined inverse, right? So if I did not have these functions being bijections, if they were, say, for instance, not injective, then f wouldn't necessarily have a well-defined inverse. Because what would happen is I would have one element in the codomain that when I tried to invert it, it would go two different places, right? And that would not be a function. But since we have a bijection, that means that we can nicely define an inverse for every single element in S omega, right? So inverses are just inverse functions. So if like, so I'll say, maybe I'll write this way. So for, so if f goes from say x to y, then f inverse is just going to take every element in y and send it to x, right? And that's still a function from omega to omega, right? Because the domain and codomain are the same exact thing. Okay, and so those are my inverse functions. And of course, if I compose f with its inverse either way, I end up with the identity map, right? Yeah.
So identity, what does that say? It's saying that like each value in x goes to that same value.
Yes, exactly. It's saying keep it fixed.
So like 3 goes to 3.
Exactly. Exactly right. Good. The questions? So it's not saying everything goes to 1. It's saying keep everybody fixed. Very good. Okay, and so yeah, we could do this for any set omega, but more specifically, we usually do this for, we just usually take sets of n numbers. And so when I take omega to be the set of, the first n integers, then we usually denote this as Sn, and it is the symmetric group of degree n. This is degree because it's that degree or maybe the symmetric group on n elements, you'll sometimes say or hear said. But it's not the order of the group, because the order of the group is the number of permutations, right? The group is a set of permutations, and the order of the group is the number of elements in that group. And so in fact, if I want to know, well, what is the order of Sn, right? This is the number of permutations of n elements. And this thing we can even kind of sketch out if I wanted to take a function, some permutation, and I go from 1 to n, and I'm going from 1 to n, right? I want to know like how many of these can I possibly have, right? So one way to define a sigma is I'm going to choose where 1 goes. And how many choices do I have here for where 1 goes? N choices, right? So this is n choices. So I fix 1, right? So maybe I send one to something like, I don't know, I, whatever I is, right? Now I do the next thing and I say, what happens to 2? And how many choices do I have for 2? N minus 1 choices, right? This is now n minus 1 choices. So altogether, anytime I define a new element, or I'm trying to define a new permutation, I'm going to have n times n minus 1 times n minus 2 times n, right? There are n factorial, sorry. N factorial. Okay. So that means the size of this group is n factorial. Good. Good. Questions? Does that make sense intuitively? Okay, so that's the order of the entire group. And okay, so what are these elements? They're functions. When we're talking about Sn, they're functions from, the set of n integers to the set of n integers. And there's a nicer way to write these functions, which is called cycle decomposition. So what is a cycle? It's a shorthand way of writing these permutations, right? So let's say I chose a particular sigma. Hate this board so much. Why is it like this? Let's say I chose a particular sigma, and I'm going to send 1 to 2 and 2 to 3 and 3 to 4, something like this, right? And I will send n back to 1. Okay, so I can define and say where every single element goes, and there's a shorthand way to do this, and that's what this a cycle does. So a cycle is going to be just a string of integers, which represents an element of Sn. So it represents one of these permutations, which cyclically permutes the integers, which represents an element of Sn and cyclically permutes the integers. Okay, so what does this look like? If I have a cycle, so an example of a cycle is something like this, where A1, A2, all the way up to AM, these are just examples of integers. So maybe this is 1, maybe this is 3, maybe this is 7, for whatever my set is here. And so how does this cycle work? What it says is that AI, so like A1 is being mapped to A2. So when I put these two things next to each other, it's saying, what is my sigma doing? It's sending A1 to A2. And what is A2 doing? It's being sent to whatever the next element is, like say A3, whatever. A3 in here just to get clear. Okay, so this is, come here. Cool. So it sends AI to the next element in whatever this list is, to AI plus 1, right? So maybe this is actually a better example here. Maybe let's say this is at, maybe let's say it's like 3, 5, 7, this, and then 2 or something like that. I don't know. So what is this permutation? How would I write this in permutation notation or cycle notations? I would write sigma as, well, the first thing I'm just going to say, where does 1 go? 1 goes to 3, so that's the thing I'm writing next. Okay. And then 3 goes to 7. Yeah, so that's the thing I'm writing after that. I was like, did I write something wrong? And then where would 7 go? I think it's probably like 9 or whatever. I don't know. And then, you know, we get all the way through, right? And then the last thing would be that it would go to 2, something like that. Well, it's hard to do in a, right? Something like this. Wait, I should probably have chosen like a finite example just so we can, let's just say I have this permutation. And then I'll say like, wait, 1, 2, 3, wait. Oh, wait, shoot, now I have to go to 7. And we'll say 4 goes to 4, 5 goes to 5, 6 goes to 6, and 7 goes to 1. That's what we're going to do. Okay, we're doing that. Let's say that's my permutation. There we go. Better example. What happens when you try to come up with examples on the fly? Okay, so here, yeah, sorry, this goes 1 is being sent to 3, whereas 3 we said is being sent to 7. 7 we said is being sent to 1. So 7 is being sent to 1. That's this next thing. So this is AI is sent to AI plus 1, except for AM is being sent to A1. So this is for I between 1 and okay, and m minus 1. Yeah, m minus 1. Is that including? No, yeah, that's right. Okay. So 1 is being sent to 3, 3 is being sent to 7, 7 is being sent back to 1. What's happening with 4? It's staying fixed, which if you wanted to, you could write it this way. What's happening with 5? It's also staying fixed. So I can write it as just 5. We usually end up, if things are staying fixed, just not even listing them. And 7 is being sent back to 1. So I could really write this way, or I could add the 4 in parentheses, 5 in parentheses, 6 in parentheses if I wanted to. Sorry, does that make sense? I did that sloppy. Oh yeah, and 2 goes to 5. Oh, thank you. 2. Oh wait, but I have to fix something because I wrote messed up. This has to do something, right? I'll just say it goes back to 2. Thank you. Good catch. because otherwise it wasn't a bijection. Perfect, good. So that is what happens with two. Perfect. Any other weird things I did with the example, or we have questions on it? Okay, great. So here, so this is a cycle. And so yeah, for this example here, that if I have this cycle 2, 1, 3, what this says is that this is the function that sends 1 is going to 3, 2 is going to 1, and 3 is going to 2, right? Okay, and so what did I say? I said yes. Okay. So I think as we can kind of see with this example, for every single permutation in Sn, I mean, this isn't a proof, but just an explication of what's happening here. Whenever I have one of these permutations, I can always group it into little, what we call K cycles, or grouped into smaller K cycles. So what does that mean? It's like any permutation can be really written as, well, maybe one of these A1, A2 to say AM1s, and another, there could be more little cycles, just like I have with this example. I have, here's a 3 cycle and a 2 cycle. So, oops. I don't want to write this. I don't want to write this. Not A1. Oh, yeah. Notation gets really messy, but it's basically that I can just write any permutation as and then some of these K cycles. Here we go. I'm gonna write this. Cool. Just kind of verbalizing what's happening with this example here. Okay, and so for an example here of what, another example of what, how I would go from a permutation like this to writing this out as K cycles. Here we have this guy, let's see. So this sigma, or maybe I'll call it tau or something, just so there's no confusion. So tau here is something in the permutation group S13, so the permutation on 13 elements. And so the convention is usually to start with 1, just because it's a nice place to start. But you can kind of do whatever you want. Just start somewhere so you don't forget where you're going. So I look at the element 1 and I say, where does 1 go to? Well, it goes to 12. And then I look at where 12 goes to, and it goes to 8. And then I look at where 8 goes to, that goes to 10. Where does 10 go to? It looks like 4. And then 4 goes to 1, so what do? Close it, good. And now I say, okay, I haven't listed all of my elements. So what should I do now? 2, yeah, so where does 2 go? 13, and 13 goes back to 2, so that's a nice little 2 cycle. And then, yeah, we haven't picked 3 yet, so 3 goes to, I picked, there is no 3, so you could do this, or, oh, I just didn't write down 3, because, cool, well, there's no 3 in S13, it turns out, but we'll just pretend it stays fixed. Let's see, we have 4 already. We don't have 5. So 5 goes to 11, which goes to 7, and 7 goes to 5. And 9 goes to 6, and 6 goes to 9. Did I miss anybody else? I think we got them all. I think they're Pokemon. We got them all. Okay, good. Okay, so so yeah, up to you whether or not you want to include the fixed cycle that I just completely forgot to write down. But here is an example. This is a 5 cycle. This is a 2 cycle. This is a 3 cycle. And this is another 2 cycle. That's how we refer to Okay, so this is referring to the length of the cycle, and the length of a cycle is just the number of integers which appear in it. Okay. Great. So the length of the first cycle is 5, then 2, then of course 1, I guess, but 3 and 2. So one thing to note is that we're going to, of course, be composing these cycles, or we're going to be composing permutations, because the group action on Sn is function composition. So we'll want to compose two functions. And so when we compose them, we'll sometimes end up writing cycles next to each other. Did I do this in an example? I think I did. I did it in an example in a moment. But what we'd like to do is then every permutation we can then write as products of, or as compositions of disjoint cycles. So what are two disjoint cycles? A disjoint cycle, or cycles are disjoint if they have no numbers in common. No numbers in common. So let's look at an example of what we mean. Okay, so I guess, for example, the thing that we have written here, tau, that's definitely a disjoint cycle. Anytime you write down one permutation, it's going to be, you can write it as a disjoint cycle, like we did here, meaning there's no 5's never repeated, 2's never repeated, 13's never repeated, none of those are repeated. Same thing with this example here, right? These are a disjoint 3 cycle and a disjoint 2 cycle. So for instance, if I'm looking at S3, I have, this is the set of permutations on 3 elements, right? So this is the permutations on 3 elements. And so what are the things in this group? Well, there's the identity permutation, which I'll just write as 1, or you could call it I, or whatever you like. There's the thing that just swaps 1 and 2 and leaves 3 fixed. There's the thing that swaps 1 and 3 and leaves 2 fixed. And there's one more 2 cycle. What's the other 2 cycle? Swap 2 and 3, very good, and leave 1 fixed. Good. Let's see, that all leaves something fixed, but I, of course, don't have to leave any element fixed. I could send 1 to 2 and 2 to 3 and 3 back to 1. So I could just do that little loop, right? And I think there's one more. 1, 3, 2. Very good. I think that's right. And of course, there's other ways I could have written them. Like this cycle is the same thing as if I wrote 3, 2, 1, right? Those are the same exact cycle. I just wrote the elements in a different order. But other than that, those are my 3 elements, or my 6 elements, right? And we know that should be all of them. How do I know that I got all of them? 6, right? 3 factorial is 6. Very good. Okay, cool. Great. So those are the disjoint cycles on 3 elements. But where are my cycles not disjoint? Well, maybe what I could do, right, when I look at S3, how do I make a new element, or to S3 is a group, right? So that means I should be able to compose multiple cycles, 2 cycles, and I should be able to get another element in S3, right? So let's see what happens when I compose, let's say 1, 2, 3, and let's say 1, 2, and maybe even 3, 4. Oops, no, let's not do that because that's not, this is an S3. I'll just do this one. Let's do this. Okay, so what should happen is I should be able to compose 2 elements, and I should get into S3, right? And I should be able to write this in this form. It's not clear that this thing is going to be an element of S3. But it's also not disjoint cycles, right? Because I have 1 and 2 both repeated in here. So let's figure out what happens, how to rewrite this as a disjoint cycles. that make sense what I'm saying? Okay, so what I'm going to do is I'm function composition, right? So I'm going to work inside to out. I'm going to go this direction because we're doing function composition. So let's just think about what happens with 1. We always ask ourselves, what about 1? What is 1 doing? 1 is going to 2. And then 2 is going to 3. Very good. So this is going to 3. Okay, now I ask myself, what is 3 doing? Well, there's no 3 here, so 3 is fixed. And then 3 is going to 1 here. So that means this S. So when I compose 1, 2, 3 and 1, 3, or sorry, 1, 2, I actually get this element. I can, of course, do this the other way and say, what happens if I take 1, 2, and I compose in the opposite order, right? So let's see. Let's now think about where 1 goes. 1 goes to 2. But 2 goes to 1, right? So here 1 is being fixed. Do we see that? We work on the inner thing first because we're doing function composition. 1 is going to 2, whereas 2 going back to 1, so 1 is staying fixed, right? Always work right to left. Now, okay, I don't have to write that if I don't want to. But what about, where is 2 going? To 3. So 2 is going to 3 here, and then there's no 3 here, so it's just staying at 3. And then 3 should be going to 2, but let's double check. 3 goes to 1, and then here 1 is going to 2. So 2, 3. Cool. Questions? No? Feel okay? Okay. Great. So we see, okay, well, we didn't prove that it's a group or that this, closure holds in this way, but right, or, not a rigorous proof, but we just kind of checked, yep, I take 2 compositions and I get a third composition. Or I get another element in the group, right? 2 functions that I compose them and I get a new function, right? And we often just like kind of drop the dot in here when we're doing the function composition. So I had the little circ in here, but we usually don't write it. So the book doesn't write the circ there. They just write it like multiplication. If you want to write the circ, great. It is function composition. If it helps you remember how that works. Sometimes it helps remember you're going from right to left. Cool. Questions about the example? Can we deduce anything about the group from this example number 2? It's not abelian. Very good. Yeah. Ooh, look at this thing. Oh yeah. S3 at least is non-abelian, and in fact, Sn for any group is for any number n is non-abelian. Very good. So it's a group because we're gonna be closed. So under function composition, I should say under function composition, just to be extra clear. For all n, but it is not abelian for any of the n's. Okay, great. Okay, great. Questions? Okay, a couple other small notes about Sn. So we talked about the length of a cycle. The length of the cycle is just the number of elements that are in that little cycle, right? So, oops, shoot, come here. So the length of, sorry, my pointer is lost. Oh yeah, so we said this is a length 5 cycle or a 5 cycle. That's also going to be the order of that. If I was just looking at this thing as its own element, not all of tau, but if I just had this is a permutation, right, on, I don't know, at least S12. The order of this element is going to be the number of elements in the cycle, right? So 1, 2, 3, 4, 5. So this is an order 5 element, right? Maybe I can't. But this is going to be an order 5 element. And you can kind of tell because if I try to compose like just this 5 cycle with itself 5 times, that's what's going to eventually get you back to your identity. So something to kind of play around with. Obviously, we won't do it with 5, but maybe we can do it with a simpler example. Let's see. If I do 1, 2, and I compose that with 1, 2, let's see what happens here. In the first thing, 1's going to 2. In the second thing, 2 is going to 1. So 1 is staying fixed. And what's happening with 2? 2 is going to 1, and 1 is going to 2. So 2 is also staying fixed, right? Or this is really just the identity, right? And so we can see as this like basic example, we have a 2 cycle. What's the order of that element? It's going to be 2. And this generally kind of holds. And in fact, for any cycle, the order of any permutation is going to be, well, sometimes I'm going to have multiple k cycles in one permutation. And so then it just turns out to be the least common multiple of each of the lengths of each of the k cycles is the least common multiple So the order of any permutation is the least common multiple of the length of its disjoint cycles. So for example, if I look at tau above, and I want to know what is the order of tau, it's going to be the LCM of 5, 2, and 3, which I think is just 30. But stop me if I'm bad at multiplying things. Okay. Great. Okay. What else was I going to say? One other little note that I'll make, unless there's any question on the order of the cycles so far for permutation, is that disjoint cycles. So if I have things with no common integers repeated, those commute just fine. It doesn't matter what order I put them in, right? It does commute, so yeah, disjoint cycles. It doesn't matter which one you start with. But only the disjoint ones, right? Because we saw here that not all cycles commute. Okay. Question. Okay, so there's some examples, and if you're not used to seeing this cycle notation, I probably could have even put some more examples in the homework of getting you comfortable with working with this cycle notation. I think there's a few more examples in Dubbin and Foote that warm you up to it, which are kind of nice. So I recommend playing around with those, and you're obviously welcome to ask me questions about them, even if I did not assign them. Cool. Great. I think 2 more little examples that we'll have of groups that are really common. So one thing that you've you've probably seen in your linear algebra class are matrices. And we can take collections of certain types of matrices, and those things will form a group. And so the most common one is called the general linear group. But in order to define the general linear group, we have to talk about it on a smaller set. I have to take elements from a smaller set. So often, maybe from your linear algebra or what have you, you're used to seeing matrices with entries that are real numbers or maybe integers or something like that. And so we need to define what are the entries going to be. And yeah, maybe just pick your favorite. Maybe it's the real numbers, maybe it's the complex numbers, maybe it's the integers. But all of those are kind of be different examples of instances of a matrix group. And so what do I want the inputs to be in general on a general linear group? I really want them to actually be a field. And what is a field? A field is a set together with 2 binary operations, not just one binary operation. So when we were talking about a group, we have one binary operation, we pick one, right? We say this one's a group under addition or this one's a group under multiplication. Here we need both addition and multiplication. And in both cases, basically what we get is a group out. And we want to make sure that they work together nicely. So I have two binary operations, plus and times, on F, so that when I look at F and plus, say F plus is an abelian group. So it's not just a group, it's also commutative. So I want F plus to be an abelian group. And usually we call the identity 0. And I also want, well, I want F and times to be an abelian group, but I have to be careful because 0 is always a problem when I'm making a group under multiplication, right? Because it doesn't have an inverse, right? So I'm going to remove 0, and then I'm going to say that thing is also an abelian group. With a different identity, which of course we're just going to call 1. Okay, and the last thing I need, so I basically have like a group structure working in two different ways, right? I have the same set, basically, that is a group under the addition thing, and it's a group under the multiplication thing. And then I want to know, how do those two operations interact? Well, they interact how you usually like them to interact, distributive property. Okay, so, and the distributive law. So what does that mean? It means the thing you think it means. So it means when I take A and I multiply it by B plus C, I get A times B plus A times C. Cool. Great. So some examples of fields are things that, we use all the time, right? So many of the examples we talked about on the first day were examples of groups under addition and groups under multiplication. So like we said, the real numbers, right? The integers are not, right? Because they are not a group under multiplication. So the real numbers, but the rational numbers are just fine. The complex numbers are just fine. And in fact, Z mod PZ for P of prime is also an example. So we usually call this FP. It's a finite field of order P. Cool. If I take Z mod NZ where n is not prime, then all of the multiples don't necessarily have inverses, right? We don't necessarily get a ring under multiplication, right? I have to do more than just remove 0. I have to remove all the stuff that's relatively prime to n. And that's why we choose PZ. Okay, great. Questions so far? Okay, so that thing is what a field is. And the point with the field is that what we're going to do is these are the kinds of things we can put into our matrix so that when I have the elements, so that when I actually do my matrix multiplication, my thing will turn out to be a group. Okay, so what is GLNF? This notation means this is the set of all matrices, which I'll call big A, where A is an n by n matrix with entries from whatever this field is that we put here. So this little n is representing the size of the square matrix. F is representing where the entries are coming from. So if I put an R here, it means they're real numbers. If I put C here, it means all the entries could be complex numbers. But I need one thing in order to make this set a group under multiplication. So I'm going to take a set of matrices and I want to multiply them. And I want to multiply them in a way that it's going to be a group. means I have to be closed. Okay, seems fine. What do I need to worry about? Inverses. And that tells me, what do I need? Perfect. I need determinant non-zero. Very good. Perfect. Fabulous. Okay, great. So I need determinant to not be zero because I want to make sure that all of those things are invertible. Okay. So this thing, so this is the general linear group of degree n, and it is a group under matrix multiplication. Okay. Great. So one thing I'll say is we said something about the, so we use the determinant here of A. And we definitely know what determinant means when I'm taking real numbers because you've done this in linear algebra, I hope, right? And probably you could naturally extend that to, I mean, definitely you could do it with Q, I guess. But even in FP, it means like basically the same thing, then just work in that group modular arithmetic, right? So determinant is basically defined to be the same way you would define it over R, right? So just take the small determinants and however you define it with your whatever method you use. Okay, so great. So determinant of A is computed by the same method. So great. So you basically use the same algorithm and then just respect your group closure and stuff like that. And then the other thing to note is that also that if you take the determinant of A times B, this is equal to the determinant of A times the determinant of B. And that's kind of what's giving you this closure, right? That's and so if the determinant of A is non-zero and the determinant of B is non-zero, then I don't have to worry about taking the determinant of the product and that being zero and popping out of the group, right? Great. And same thing with invertibility, right? I guess. Cool. Great. Any questions? Okay. Was I going to say? Oh, I was going to put that down here. That's why. Okay. One other little thing that I think your book doesn't mention this yet. There's other subsets or subgroups of GLN that come up pretty regularly. There's many that I'm not even going to try to mention all of them. There's different like the special orthogonal group and all of these other things, but one that does kind of come up fairly regularly is, so this is the GL stands for general linear group, bless you. So on n by n, so like those n by n matrices. SL is the special linear group. This is a subset or a subgroup of GLN. And we just specify that instead of the determinant being non-zero, it's specifically 1 or sometimes plus or minus 1. I can't remember which one, GL and or PSL and which one's SL, but sometimes you'll see that you can specify the determinant's 1. This is also a group. Under matrix multiplication. That's all. Great. Okay. Last major example that kind of shows up in one of these sections is the quaternion group, which your book denotes with an Q8. And there's one example that has you show this, but how they define the quaternion group is a little bit messy. It's just an 8-element group, and it has these 8 elements, plus or minus 1, plus or minus I, plus or minus J, plus or minus K, but they have to obey a bunch of different relations. So one of the things is that, yeah, 1 acts like your regular identity. Sometimes that will be denoted with a different letter, but 1. -1 acts like you think -1 usually does. Right? So it's negates everything. And when I multiply -1 by itself, I get 1. But the interaction of I, j, and k is a little bit weird. So when I square I, you can think of it just like the square root of -1, where I square I, I'm going to get -1. Same thing with j and k. But they also interact in this really weird way where I times j is equal to k, but j times I is equal to -k, and so on. So there's all these different relations that hold. And one thing you can see immediately from these relations is this group going to be commutative? No, right? Because I can see right away that ij and ji don't give me exactly the same, right? Or sorry, it's not a billion, means, right? Good. And so one of the exercises in your text has you write this in terms of what is it called? Representation. Wait, is that what I want to say? Group presentation? Is that what I want to say? I think that's the word, right? And so I need to have I need to have 4 generators for this group. I think it's -1, I, j, and k. Because once I have k, I also get -k, right? By multiplying by -1. And I also have 1 by squaring -1, right? But I also now have to say what are the relations that hold between all these things to show that these are actually generators. Well, I need for -1 squared to be 1. And then I need to say that I squared is equal to j squared is equal to k squared, which are all equal to -1. And that's also equal to I times j times k. And those are the minimal relations that I need to state hold for I, j, and k in order to get all of these. And so I think if I remember this exercise properly, I don't think it was required, but it was just a suggested exercise. I think what you need to do is basically show that given just these relations, you can actually get all of these other ones as well. Okay, they follow directly from just these generators and these relations and the fact that the group is close. Cool. Question. Okay. We're done with boring examples. I mean, examples are great. We love examples, but just listing them is like less fun than like talking about things, right? Okay, so now we have some examples in our toolbox so we can start talking about some more interesting concepts and things of what we want to do with these groups. And one natural question that comes up once we have a bunch of different examples is, when are these examples actually really the same thing? When are 2 groups actually giving me the same structure, but maybe with a different notation, okay? And that's really the first question we want to try to address in this next section, which I won't have time to go through the whole thing today, but we'll kind of introduce, is we want to ask ourselves, when are 2 groups the same? In other words, we want to characterize when 2 groups have the same group theoretic structure. So what we're asking about is like the structure and not so much the elements, right? Okay. And to do this, what we need to use is the notion, we need to use functions in order to say, what we'd like to be able to do is I might want to say something like, hey, G and H, they might have different elements. They don't even have technically different operations, but they feel very similar. And how do I go from one to the other to say that they might be the same? What am I going to do to each of those elements? And what am I doing to each of those elements to say that they might be the same is I want to think of like, what's a map to go from the elements here to the elements there that tells me that the structure is the same. And so that's the first notion that we need here is the notion of a homomorphism. So if I have 2 groups, G and H, they might have different operations. And we have a map that I'll call phi that goes from the set G to the set H, such that if I take phi on whatever my group elements of G are, so let's say G1, well, the operation in G is star, then what I get is that phi breaks down under the same, kind of with respect to the same structure in H, right? So notice that these are elements of H. And what we're saying is that the operation that happened over G is respected in H by the vector. Okay, this thing is called a homomorphism. So this notion is called a homomorphism. Great. So it's a map that what we're having, so right, each of these things is in G. If I perform the operation in G and I send it to somewhere else in H, what it actually pops out is something that had, like, if I were instead to have just performed this operation on G, or sorry, this function on G and this and the function on G here, it would respect the operation on H. That's what the homomorphisms do. Okay, and so two things are going to be isomorphic, or this function is going to be an isomorphism if that homomorphism is also a bijection. So I'm just going to say if one phi is a homomorphism, and two, phi is a bijection. Okay, great. So sorry, so a bijection meaning injective and surjective. Okay, and that's going to be our notion of the same. When I have this isomorphism between like a group G and H, it can exhibit a function that is a homomorphism and is a bijection. Then I'm going to say two groups are isomorphic, or meaning they're the same. They have some sort of same structure. Okay, we'll talk more about what that means and how that applies next time, but that's a basic definition, and like we'll do examples and stuff like that. Okay. So next time at the end of class, we'll have our first little quiz. It'll mostly be definitions and things like that. There's not maybe even that many intense definitions in my brain, so know the definition of a group. But if you have questions, let me know.